Hey guys, welcome back to my YouTube channel. Today we're going to continue on the concept that we discussed in my first CCNP video, the second overall video of this channel, which is redistribution. So in that video, I kind of gave you a Day 1 guide to redistribution, and I explained to you what it was and why we would want to take routes from one routing protocol and redistribute them, translate them into another routing protocol so that they can be natively understood by routers in that routing domain. I explained the uses that that could have, and today we're going to cover the practical aspect of it. Before I get started, I just wanted to go ahead and say I finally got my CCNP Enterprise. So I passed my route exam on my third try. Thank God I didn't have to go for a fourth because I literally would not have had time. That was my last shot to pass it. So I am now a CCNP RNS that has been upgraded to a CCNP Enterprise. So yay! Go ahead and look out for blog posts on the matter. I'm going to go ahead and post a screenshot on my blog as well as a link to it in the description below. If you want to go ahead and check it out, I do have posts on those exams coming up, and I definitely am not happy about route. So, anyway, with that out of the way, we're going to go ahead and hop into the meat and potatoes of this video, which you can see in this topology over here. So I've already got this kind of running. This is just, again, like I mentioned in the first video, you don't have to have router 5 here. So router 5's purpose in this particular topology is to bridge the EIGRP and the OSPF domains. You don't have to do that, and most times you would have a single router that's maybe running EIGRP and OSPF. Maybe router 1 gets moved over here or something and has a connection to OSPF. But I'm using a separate router as we call it the ASBR, or the Autonomous System Boundary Router. The router is actually doing the redistribution. I'm using this router just so you can better visualize what's going on as you're learning about redistribution. So if I bring over my secure CRT window here, hopefully you've gotten a good idea of what the topology is. I've got two routers that are running EIGRP in AS1, and then OSPF, since its process ID, I'm running in area 0. So if I go on, I should probably name these, but mind you, they are named here, so OR1 or ER1. Oops, if I can type ER2, OR2, and this is the border router. Yep, BR is the border router. Okay, so if I go on this router, it's actually not R1, it's R2. If I go show run EIGRP topology, you can see I've got two routes that are being advertised. These are passive routes, so passive in the EIGRP, meaning that the routes are stable. I've got routes coming from 192.168.1.1, which if I do a show IP interface brief, you can see is router 1. If I go to show IP EIGRP interface, you can see I've got loopback 0, gigabit ethernet 01, and gigabit ethernet 02 advertised into EIGRP. So if I do a show IP EIGRP topology top, you can see that I've got all these routes that are via connected. So they're being directly advertised into EIGRP, and you can see if I do a show IP route EIGRP, that it is indeed receiving those routes. It's actually receiving all three, as you can see here, but one of these is the connected route. Yep, here. So it would already have the connected route. So that's why it's only showing 2 EIGRP routes, even though there's 3 advertised. It's an administrative distance thing. Hopefully that should be a review from your CCNA. Anyway. Coming back around though, OSPF, similar thing. R1 has a bunch of routes that's advertising out to R2, show IP OSPF interface brief. You can see loopback 0, gigabit ethernet 01, and gigabit ethernet 00. So in each of these cases, I'm advertising the loopback in router 1 and router 3. I'm advertising both of its physical links, so here and here, and I'm advertising the virtual loopback interfaces that are on each of the routers. And router 2 is receiving all of it. Alright, so what you'll notice is this 10.10.10.10 address and this 1111 address, if I try to ping, say I try to ping even from OR1, if I try to ping the loopback on ER1, EIGRP R1 from OSPF R1, you'll see that my ping fails. That will change by the end of this video. By the end of this video, OR1 is going to be able to ping that address and succeed. Now, why does that happen? What is another way we could solve this besides redistribution? Well, the problem is we don't have a route for it at all, right? It's trying to get to 1111. It's looking at its routing table. It's like, mate, I have no route for this at all. I have no idea how to get to it. So there's a lot of solutions to this, actually. OR1 has the liberty of being connected through R5 to, or R3 has the liberty of being connected through R5 to R1. So what I could do if I wanted to is say, okay, well, let's look at the IP addresses over here. G01 is going to be the interface connected to the border router. What I could say is, well, IP route 1111, it's a /32, so I'm going to give it a host subnet mask, and then say 10.0.0.1. This should have reachability through maybe a similar issue to, I may have to make a route for it too. 10.0.0.0. Actually no, 255.255.255.252, and then to the border router, so 10.0.0.6, and something similar in this case. I'm going to, on ER1 IP route 10.0.0.4, 255.255.255.252, 10.0.0.2. If I do ping 10.0.0.6, that should work. Yep. Or ping 10.0.0.5, I'm sorry, is the address I should be pinging from this router. Alright, and it works. Same thing here, if I ping the address 10.0.0.1, alright. So now my static route should be working. So if I ping 1.1.1.1, alright. So you can see, if you're confused by what I did there, completely understand, let me walk you through it. So what I did is Gigabit Ethernet 01, if I go ahead and expand this part of my topology here, expand all, G01 on router 1 and router 3 connect to this border router here. So what I basically did was I gave router 1 and router 3 reachability to each other, right? Because by default they don't have routes to each other, they have routes each to router 5, connected routes. I gave router 1 and router 3 reachability to each other through static routes. And then I said, okay, well, let's put a static route in, 1.1.1.1, 255.255.255.255, 4 255s, and I said, okay, well, use a static route to get to it. So via 10.0.0.1, and how do you get to 10.0.0.1? By going through 10.0.0.6, which you have a connected route to, right? So you have this 10.0.0.4/30 connected route. So it's kind of it's a roundabout process. So that's not necessarily what we want, right? We want to use our dynamic routing protocols to get full reachability, but we don't want to use these static routes, right? We want to use dynamic routing protocols so that if 1.1.1.1 goes down, the router stops redistributing it, and the entire topology converges and now knows that 1.1.1.1 does not exist anymore and removes it from the routing tables. That way we don't black hole any traffic. So let's go ahead and remove the static routes. Just go show run in section IP routes. Alright. Just going to undo what I did there for a second. Show run section IP route. Oops. Or show IP route static. I'm just gonna make sure that all my static routes are in the routing table. Alright. So if I ping 1.1.1.1, it doesn't work. Alright. So now what could we do? Well, we could go back to redistribution. So in the redistribution concepts video, I went over how the routing protocols don't understand each other, right? EIGRP does not understand the metrics of OSPF. If I go to show IP route OSPF, or wrong router to be doing that on, if I do show IP route OSPF, which I've already done here, you can see I've got a metric of 2, right? EIGRP has no idea what that is. Now, we as humans, we as network administrators know that's cost, right? We as network administrators know, okay, there's a default auto cost reference bandwidth of 100 megabits, and it's going to be calculated based on that, right? So it's a operation that involves the bandwidth of the interface, but that's not necessarily known, right? And in fact, it's fairly easy to see how it would produce a metric of 2. This is a gigabit Ethernet interface, so 1000 megabits. If you've got an auto cost of 100, yeah. So it's fairly easy to see how, or 100 megabits. It's fairly easy to see how we would produce a metric of 2 here. What's interesting then about this is try telling EIGRP that. EIGRP, if you'll recall from your CCNA studies, uses the concept of a composite metric, right? We have these different K values that correspond to, okay, this complex algorithm, this complex equation that basically has bandwidth, load, delay, and reliability. Not necessarily in that order, or actually, yes, in that order, sorry. So, now OSPF doesn't understand that. You tell OSPF there's 5 K values, OSPF will be like, K values, what the fuck are you talking about? Just use cost, mate, right? So it's really difficult to just take routes and move them over from one routing protocol to another without using some form of translation, right? Redistribution at its core is just translation. You're taking routes of one kind of metric and you're converting them to another. That's all it is. Now, that works even with our non-dynamic routing protocols. Connected routes and static routes come to mind. A connected route doesn't quote-unquote have a metric. It has the metric components. If I run show interface gigabit Ethernet 01, I have bandwidth and I have delay. For default EIGRP, that's what you need. Alright, you got reliability here, right? So for default EIGRP, that's what you need, right? K1 bandwidth, K3 delay. OSPF uses the bandwidth. There you go, you got the bandwidth right there, right? So if you redistribute a connected route, it can just pull off the interface what it needs to make a metric, right? Static routes don't have a metric. If you make a static route, like we did earlier, if I scroll back up to where we had the static routes, this metric value is a 0. A static route doesn't have a metric. You can define a number at the end of your static route statement, but that's to define the administrative distance so that you can create what's called a floating static route. So, what can we do about that? Well, we have to go to our border router. So again, if you remember in the first video how I mentioned the router that's actually doing the redistribution is going to be called your autonomous system boundary router. So in this case, it's going to be the router that sits on the edge of each of these routing domains. So I visualized the routing domain with multicolored circles here. Yay! So we have this green circle here, and we have this red circle here that represents the EIGRP and the OSPF routing domain respectively. So we have to go to a router that's sitting in between them, that has a connection into both routing domains, and do our redistribution there. In this topology, that's going to be R5, which is our border router. So because I do a show IP protocol, or show IP protocol, we have OSPF1, and we have EIGRP1. If I do show IP OSPF neighbor, we have one neighbor. If I do show IP EIGRP neighbor, we have one neighbor. So, we're going to do something called mutual redistribution. And I may have covered this in the first video, I don't remember. But in short, mutual redistribution is a bidirectional redistribution. We're going to redistribute EIGRP into OSPF and OSPF into EIGRP. There are cases where you might want to use single direction redistribution, so redistribute into one routing protocol but not the other. But this is one of the more common scenarios when you're doing redistribution, mutual redistribution, because you want to ensure full reachability. You want to ensure that if OSPF knows about an EIGRP route, most likely you want EIGRP to know about the OSPF route as well. So we're going to go ahead and configure mutual redistribution, and that involves going into each routing process and redistributing into the other. So this is one of the mistakes that some people make when they're first learning redistribution. Is, well, where do I do redistribution? Is it from the routing protocol that I'm redistributing from, or that I'm redistributing into? Well, it's the routing protocol that you're redistributing into, because your redistribution statement will contain the routing protocol that you're redistributing from. Let me explain what I mean. Let's say I'm redistributing into OSPF, so now I want to do EIGRP to OSPF redistribution. Okay, well, I would type in router OSPF1. So after I type in router OSPF1, my next step is to type in the redistribution command. And the redistribution command is, wow, redistribute. Alright, what routing protocol? You can see we also have a source VRF if you need to specify that for your environment. Okay, well, let's see. We are using EIGRP. So we're in OSPF mode, and we're going to redistribute EIGRP. What AS number are you using? It's very possible that you have multiple EIGRP processes running on the router, each with their own independent set of routes. What AS number do you want to use? 1. Alright, and I'm using 1 because my EIGRP AS here is 1. This is the output from the show IP protocols. You can see EIGRP 1, EIGRP AS 1. And we have a bunch of options here. These options, it is important to note that it is dependent on two things. 1, the routing protocol that you're actually redistributing into, and 2, the address family, the IPv4, IPv6, because IPv6 will have different options. Particularly when I'm looking at list, it'll be a list option right here. That's different. And for IPv4, this option is super important, because here's what subnets does, right? Let's say, I'll do it without subnets just to show you. So I'll just say CCR complete request. And now I'm redistributing. If I do show IP protocol, right, show IP OSPF1, this is how you can verify redistribution. Well, firstly, it is an autonomous system boundary router. You can tell from that statement alone that this router is doing some form of redistribution. And what is it redistributing? EIGRP1. This shouldn't actually be there. It includes subnets and redistribution. I didn't specify subnets. Interesting. It's actually including the subnets keyword. I don't think it should be. Interesting. Alright, I probably won't be able to show you this. Let's go to, let's go here. I need to see this real quick. Alright, that's unfortunate. So, let me just, I won't be able to show you, but I will explain what the subnets keyword does. If you have a version of iOS that actually lets you not include it, I didn't realize that this router would not let me not include subnets, right? That just goes to show you how important it is. Here's what subnets does. OSPF is a very old protocol. And so it was released when you still had classful blocks, right? So what the subnets keyword does is it says you are allowed to redistribute subnets. So you kind of saw a sneak peek of that when I didn't intend to let you see a sneak peek of that in this output here. Redistributing external routes from EIGRP 1 includes subnets and redistribution. So let's face it. If you're an enterprise network, you are not using classful network blocks anymore. Let's be honest. You're using some form of a VLSM subnet mask. You may be using a /25 or /23, depending on the size of the subnet, the size of the campus, right? So that's a problem for redistribution into OSPF, because OSPF is designed with the default intention that you will be redistributing classful networks, or networks that align with classful boundaries, which you're not always going to be. In fact, you're almost never going to be. So what subnets does is it basically gives OSPF authorization to say these subnets that I've got on the router show in G00, list 10.0.0.0/30 here, go ahead and redistribute that. Or actually, if that would apply if I did redistribute connected. Any EIGRP routes that you see, it doesn't matter if they're not aligned perfectly with a classful boundary, go ahead and redistribute it. You have permission to redistribute these subnets in, right? They don't have to be classful networks per se. So that's, you will, if not, you will almost, if not always, almost always be including that subnets keyword in your redistribution command, right? And in this case, it doesn't even, again, on the CSR 1000V that I'm running this on, or IOSV, I'm sorry, on this 15.7 IOSV router, it doesn't even let me redistribute into OSPF without including the subnets keyword, right? Now, how do we verify that everything's been redistributed correctly? I got a sneak peek while I went to route OSPF router 1, did a show IP route OSPF. It just gets pumped in a routing table of your other routers. So here's what's happening, right? Border router is taking these subnets, right, or from EIGRP that are being redistributed into OSPF. External self-originate. If you remember from your CCNA may not have covered this. If you remember from your other coverages of OSPF, you may have covered the different LSA types. You have the type 1 router LSA, the type 2 network LSA, the type 3 summary LSA, etc, etc. Well, the type 5 in OSPF v2 and v3 is the external / OSPF v3 technically calls it the AS external, but point is you have the type 5 external LSA. This is what the type 5 external LSA is used for. It's used to carry routes from an autonomous system boundary router down to the OSPF domain. So what's happening when we're doing the redistribute EIGRP 1 subnets command is OSPF is looking in its routing table for any EIGRP routes, right? Well, here's EIGRP routes right here, right? It's going into the routing table because it has to, right? It relates back to the whole concept that EIGRP doesn't understand an LSPF route, and LSPF doesn't understand an EIGRP route. That's the entire reason we're doing this in the first place. So it doesn't make sense for the border router to just go straight into the EIGRP topology table and pull out, right? That wouldn't work, right? Instead what it does, and there's other reasons for this too, but what it instead does is it goes into a global IP routing table, right? Again, that differs if you have VRF, but it goes into the routing table and it pulls out the routes, right? So that works because let's say in EIGRP, you have a route that's not a feasible successor. Well, guess what? It's not going to be in the routing table. It's not going to get hooked by your redistribution, right? So point being though, it goes into the routing table and it pulls routes out. So it's only going to pull either your load balance routes or your best route. It's not going to pull all of them for redistribution. But point being, it'll take these routes here. In the case of something into OSPF, it'll take routes for the protocol that you specified in the redistribute command, in this case EIGRP, and it'll pack them into a type 5 external LSA. And it'll send it out to the entire OSPF domain. The type 5 domain, or the type 5 LSA, is the only LSA that is allowed to sustain throughout the entire domain. You'll recall with something like a type 1 LSA, right? It gets stopped at the ABR. It is not allowed to go beyond its own area. Once it hits an ABR, well, guess what? Now we don't have a type 1 LSA. We have the main contents of the type 1 LSA that are packed into a type 3 LSA, right? And we have a type 3 LSA that's being received at an ABR. Well, guess what? It's going to go from one type 3 LSA to another type 3 LSA. And then be redistributed, or not redistributed, be spread out into that area. Well, the type 5 LSA is the only LSA type that is allowed to start from one router, in this case the ASBR in the domain. It starts from one router and it goes down the entire domain, right? Doesn't give a what area it's in, right? Start from area 2. It would go to every area in the OSPF domain. Doesn't matter what. So in this case, yeah, it's not immediately obvious when we're doing single area OSPF, but it becomes more obvious when we're doing multi-area OSPF. We have these OE2 routes. Well, why does it say E2? Let's look at our key, right? E2, OSPF external type 2. Now we have this E1 right here. Well, what's the difference? You can see our metric here, 20 and 20. So let's be completely clear on what this does for a minute, right? So in my redistribution command, as you remember, I had different options, right? If I go back up here, let's look. I had different options, right? Metric and metric type. So the TLDR, because I have to also get to EIGRP here, but the TLDR of what the difference between external type 1 and external type 2 route is that the E1 route is a more representative measure of what the actual distance is between routes. So let's kind of go into our diagramming software here, and we'll go ahead and look at this diagrams. Let's go ahead and, oops, I have an old diagram up. All right, so let's say that I've got router 1, router 2, this is a quick little diagram here, router 3, and I'm going to go ahead and connect these together. There we go, right? So we have this route here. Let's say that this blue thing is our route. So ordinarily, right, in normal routing or normal dynamic routing protocols, your metric is a cumulative. As it passes, let's say in the EIGRP, right, we have our reported distance and our feasible distance, right? So as this route passes through these different routers, right, the more routers that it has to go through, say we have router 4, if we added router 4 to this topology, right, the metric would go up. So let's say it was from, like, let's say there was a host down here, right, or actually, it'd be better to say a router down here that had this route, and let's say that 192.168.1.0 lift up here. Well, has to go to router 3, router 2, router 1, right? And in each of these cases, the more hops that we have, the more distance that we have between the router that uses this route and the actual, and the intermediary routers, the more intermediary routers we have, the larger this metric is going to be, right? So let's say this metric is 1,000, right? If I add router 4 here, maybe this will go up to 1,100. Let's actually do that real quick. So I added router 4. So now it has to go to router 4 as well. So let's say our metric goes up to 1,200 or something, right? That's how it works. The more distance that we have in between a router and the endpoint router, the more distance we have, the higher metric, right? And that makes sense. We want the shortest path available, the most efficient path to get somewhere. Well, it wouldn't really make sense, right? If you had, let's say that this was a static metric of 20, right? So let's say that this entire path has a metric of 20. Let's say we added router 5 here, right? Would it make sense to you if the metric stayed at 20? Even if we add router 5? If you said no, well then, welcome to OSPF redistribution, because that's what external type 2 means. External type 2 means, okay, I don't care what the actual distance between these 2 points are. I don't care if the actual distance between here and here is actually 150 or something. No, I'm going to use a statically defined metric. In the LSA, right, that actually contains the metric, the forwarding routers, the intermediary routers are told, no, you're not allowed to change this, right? The ASBR originates the LSA, the type 5 LSA, using a statically defined metric of, by default, if you don't give it anything else, 20, and it marks a flag in there that basically says you're not allowed to change this, right? Any intermediary routers that this is flowing through, you have to make a copy of this, put it into your LSDB. You're not allowed to add a metric to this. Who do you think you are? And then pass it down to the other routers downstream, and then same thing. So every router in the line has a metric of 20 for the route. It's not necessarily what you want. It may be what you want, it may be okay, but that's not necessarily what you want. What if you want your redistributed routes to have the similar concept of, the larger distance that I have, the larger I want the metric to grow. I want my metric to be representative of my network topology instead of just being set at some statically defined amount. That's what you would use an external type 1 route for. So let's notice the difference, right? So we have these OE2 routes. E2, by the way, is the default redistribution metric type, right? External metric type. But we have this metric of 20. Let's go on our border router here. And I'm going to go ahead and do router OSPF here. Router OSPF 1, no redistribute EIGRP 1. Let's go rerun this command, subnet, but this time I'll include the subnets keyword, and I'll say metric type 1. Now, this metric keyword allows you to define a starting metric. Now, when you're doing OE2 routes, OSPF external type 2 routes, right, because your metric is not allowed to be modified by the intermediary routers that's flowing through, that the type 5 LSA is flowing through, as I said earlier, and this metric keyword ends up being your final metric, because if you started with 20, let's say I say metric 10, right, and this were OE2s, if it started with metric 10 and it flowed down and no one was allowed to change it, by the end it's 10. If no one's allowed to change it from 10, it will stay 10, right? But if I give it permission to change the metric by saying metric type 1, I start with 10, and as I go down and down and down, it's going to add and add and add to the metric. Now I do try to route OSPF. We have this OE1, and you can see 11. Well, why is it 11? You recall, we started with a metric of 10. It went down to this router here, which added its own interface cost to the ASBR. So this router has a cost of 1 to the ASBR, which is the border router over here. So it said, okay, my composite metric is 11, right? 10 plus 1, 11. I'm including the cost that it takes me to get to the ASBR, right? And if I go back here, actually I don't need to, but if I went back here and I said metric type 2, it would just say 10, right? Let's go to OR2 and we'll see this, right? 12. So this has a metric of 2. It has a metric of 1 to get to OR1, and then it has a metric of, and then OR1 has a metric of 1 to get to the border router. So this router has a composite metric of 2 to get to the border router. It started with 10 in the Type 5 LSA. The routers are allowed to modify the metric, so it copies it into its own LSDB with a metric of 12, right? And you can see how this is more representative of the network topology. As the space grows between the autonomous system boundary router, the router that's doing the redistribution, and the router that actually has the route, the metric grows. And this is why if you have an OE1 and an OE2 route that's competing for a place in the routing table, OE1 always wins out. OSPF gives OE1's higher priority than OE2. There's a specific hierarchy to how routes are selected. It's a mess. Anyway. But point being, right, we have these metric types. Now, EIGRP, a lot simpler, right? But there is one catch with EIGRP. So I'll keep it metric type 1. The rest of these shouldn't be important. Tag is one of the ones that transfers between routing protocols. A tag actually doesn't matter for you, right? Let's say I've got router 1 and router 2, and I set a tag on router 1, and it's redistributing routes to router 2, right? Router 1 doesn't actually care what the tag is, right? Who cares what the tag is router 2? Who cares what the route, or the tag is the router that's receiving the redistributed routes, right? So you'll see this a lot on, at least the old CCNP RNS exams had a lot of tag related things. A tag is just a number, right? It can be any number you want. It can be an arbitrary number. But the important thing, right, is that the tag is used to identify and differentiate certain routes from other routes. So let's say that there's these routes with a certain characteristic that I want to match on, right? I'll give each of those routes a tag, and then on the other router, the router that's receiving my redistributed routes, that tag will mean something to it. Let's say that there's a route map on that router that says, okay, if this route has a tag of 1111, right, do not redistribute it. If it has a tag of 1111, do not redistribute it. And that's important for loop prevention, right? We'll see later. I'm not going to show it in this video because it's getting super long. But you'll see in some redistribution videos loop prevention, because redistribution can leave you prone to routing loops depending on how your network is designed and if you do it correctly. Well, a tag can be used to stop a routing loop, because you can use a tag and say, okay, the only way that this tag could have been applied, in my case maybe, is if the route was redistributed. So if I see this certain tag, I know that it's been redistributed, and I know that I should not redistribute it again, right? Back into the routing protocol that it came from. That's kind of what we would use this redistribution for, or this tag for. There's a lot of uses for it, but you can set it using a route map. A route map in IPv4, a route map has a lot of options you can use. It has a lot of flexibility. But anyway, let's complete our mutual redistribution now. So we're going to go into router EIGRP1, and what am I going to say? Redistribute OSPF. What's the process ID? Let's do a show IP protocol. Do show IP protocol if I can type today. OSPF1. So we have a process ID of 1. So redistribute OSPF1. And here actually, let's just hit enter, because this is one of the ones where I can show you that it won't work. If I go to EIGRP1, I do a show IP route. Hey, where's my, I thought I said redistribute. Let's go show IP protocol real quick. Alright. Well, it's redistributing. Let's look for this real quick. It's redistributing OSPF1. Why isn't this working? It should be, right? Let's go to router 2. Show IP EIGRP. Show IP route EIGRP. Well, no, there's no I'm looking for DEX, right? D is EIGRP, EX is EIGRP external. No, I'm not seeing D space EX in here. What's wrong? This goes back to our discussion about EIGRP using this complex metric that involves different parts. If I said redistribute connected, right? Well, EIGRP go on the interface, pull bandwidth, pull delay. You're done, right? EIGRP now has what it needs to form its composite metric, right? Again, redistribution is what we use to translate the metric from one routing protocol to another. In this case, from OSPF to EIGRP. We're translating cost into the composite metric. Does that make sense to you? But the composite metric, you may be saying, but the composite metric has so much to it. It has bandwidth, it has delay, it has all of this stuff. And OSPF doesn't care about that stuff. It just cares about this bandwidth that's on the interface. It says, okay, I'll pull this bandwidth. Good day, sir. Good day. I don't care about the rest of it. I don't care about delay. What the heck's reliability? That's what we're worried about, right? EIGRP won't know what the heck it's going to do. And this is a perfect example of that. I just said redistribute OSPF1. This JoIP protocol says it's redistributing it, but we don't have EIGRP routes because it can't form the metric. We didn't give it anything to form the metric with, right? It has all these different parts to it, and we didn't give it anything to form the metric with. That's the important takeaway from this, is that when we're redistributing certain sources, most sources should I say, the only time I can think of where this wouldn't apply is when you're redistributing from EIGRP to EIGRP. If you're redistributing like from AS1 to AS2, that's when you wouldn't need it. And if you were redistributing from a connected, if you said redistribute connected, that's the only time where I could think of where you wouldn't need it. No redistribute connected. But if, let's say in this case, we're redistributing OSPF. Let's find it in our EIGRP statements real quick, right? We're redistributing OSPF. Again, OSPF uses cost. EIGRP has no idea what to do with cost, and even if it did, cost only includes bandwidth. It doesn't include any of the other stuff that EIGRP needs. So what's our solution? We kind of have to spoon feed it a little bit. Here's what I mean. So in LSPF, right, this metric keyword, this metric 10 here, I didn't have to give it a metric because it would have just defaulted to 20. Not so in EIGRP. EIGRP, in most cases, in most redistribution cases, will not do anything at all unless you have this metric keyword. And let's give it metric, right? So I'm actually going to copy Shay off the interface. I'm going to be honest with you. Actually, you know what? Nah, I can give it whatever I want. So I'm going to give it 100,000 kilobits per second, 10 microseconds, let's say 100, 255, 255, 1, and 1500, right? So here's what I'm giving it. I'm giving it, oops, let me get my dock out of the way for a second. Oops. Get out of the way, dock. All right. So you can see the first number here is bandwidth. The second number, delay, reliability, the effective bandwidth, the load, and then the MTU. So I have all four, because K4 and K5 technically apply together, right? But we have this bandwidth, this delay, this reliability, we have load, and then we have the IP MTU. The MTU isn't actually factored into the calculation, but it's needed anyway. If I go here, now it's actually complete request. You might be wondering what match does. Match matches the type of OSPF route. So you can be very granular, and you can be even more granular with your route maps, because your route maps can have match statements. You can match based on an ACL and only redistribute routes of a certain subnet. That would be an example of why you would use a route map. Match lets you match on a type of OSPF route. Is it OSPF external? Is it OSPF internal? Is it OSPF NSSA external? And is it contained in a type 7 LSA, right, for NSSA? But we're not going to match on anything. We're just going to say redistribute OSPF1, all of it, metric, we give it a metric. Let's go show IP route EIGRP. And we can see, oh, we now have external routes. And let's go to our show IP EIGRP topology. Let's give it a prefix. 10/10/10/10/32. Would you look at that? What did we give it? We gave it our bandwidth. We gave it the total delay, so I added some delay to it. Reliability, load, MTU. And external protocol is OSPF. External metric is 2. So actually, it's nice enough to take the external data and put it in here for us. But the point being, right, we had to give it all these vector metrics because if we didn't, it had no idea what to do. It doesn't default to anything. So we had to give it to EIGRP in order for it to have any idea what to do with these routes, right? And now we have these external routes in here. So these were originally OSPF routes. The border router is doing translation. If I do IP protocol, show IP protocol here, this is one of the ways we verify our redistribution. EIGRP1, and if I go down here, redistributing OSPF1. So OSPF into EIGRP, EIGRP into OSPF. Now if I go here, right, we have these OE1 routes. So without any static routing, right, ping.1.1.1.1 was not working earlier. If I do ping 1111 now, it works. Right? Because we now have a route for it in our routing table using our dynamic routing protocol. It was originally an EIGRP route, and then we had a router in between that translated the EIGRP route into OSPF terms. And now our OSPF router can understand it. It has a route to 1.1.1.1. Now we can ping it. Same thing here. What's the loopback of OSPF R1? 10/10/10/10. Let's see if we can ping it. You can probably already tell from the fact that it's in the routing table that yes, we can. So this concludes our section on redistribution. Specifically, we covered redistribution between OSPF and EIGRP. These are honestly, at the CCNP enterprise level, these are two of the hardest routing protocols to redistribute from because they each have their own individual caches. In OSPF case, it has the different metric types, and it has the subnets keyword. In the EIGRP, you have to give it the vector metrics. The rest of the routing protocols are pretty straightforward. You got RIP, you got BGP. If you can understand redistribution into and from EIGRP and into and from OSPF, you can understand those routing protocols just fine. You'll have no problem doing it. But anyway, I hope you guys enjoyed watching this video. I hope you guys learned something. Let me know in the comments below if you have any thoughts about this video, if you have any suggestions, if you have any questions. I try to respond to all the comments I can if I have time. Go ahead and check out my blog and the other links in the description below if you want to. If you enjoyed this video, consider leaving a like, consider leaving a subscription and turning on notifications. It really helps me out a lot, and it keeps you up to date on the videos I'll post next. My next video coming up is a CCNA video. For now, I'm alternating between the CCNA and the CCNP content until I get a better schedule. But yeah, again, I hope you learned something. I'll see you in the comments below, and yeah, yeet!